let's talk a little more in depth about the position vector and how we get it. So we've talked a lot about vector addition, but this position vector is actually a form of vector subtraction. So whenever you have a vector floating out in space like this, you need some way to orient it to get its direction. So we like to imagine if it starts at point A and ends at point B, we can imagine that this is two vectors, one leading from the origin to point A and one leading from the origin. A dummy in these vectors, this is my position vector, always denoted with an R. Our position vector is going to be R. Vector 2B. And from the origin out to our position at A. Vector A. So for each of these vectors, we're going to have their Cartesian components, right? So you're going to have the vector at A is going to have an x component at A, I hat, plus the y component of A, j hat, plus the b component of A, k hat. And our b vector works exactly the same. We're going to have our b is the x component b, r hat plus the y component of b, r hat, I hat. Sorry. I hat plus yb j hat plus the z component of b k hat. There's no r hat to my knowledge. So what we do here is a vector subtraction. So to get this blue vector here, this is the position vector RAB. So it's going from A to B. It has to use this naming convention. If it said RBA, that would mean that our vector is actually pointing in the opposite direction, right? It would be the vector pointing this way. That would be vector RBA. So it's important to note which way you're orienting your vector. So we have ours oriented from A to B. Remove that other line. So to do that, we'll do a vector subtraction, which is going to look like RAB is RB minus RA, which is as simple as that. All we're going to do is subtract the components from each other, right? So your RAB going to be your x component of B minus your x component of A, I hat, plus y component of B minus y component of A, j hat, plus b component of B minus z component of A, j hat. So this is our position vector formula. We can find any position vector using this vector subtraction. And where this comes in really useful is anytime you have a vector floating out in space that usually you can orient by a few measurements, but maybe they don't give you clean angles. You don't have the angle, your alpha, gamma, beta here to go off of, orient yourself. So maybe you just have a couple of points in space and you need to create your own vector to find the information. So this is very useful for that, especially when we combine it with a unit vector. Because if we combine this with the unit vector, we can actually convert this into a unit vector. So we can say the unit vector, AB, is the vector RAB over the magnitude of RAB. And this formula is just what defines a unit vector. Before we had been just calling it F. The vector F over the magnitude F. But using this, we now have an orientation, a direction for the vector in space, which we wouldn't have before, right? If we just had some vector floating in space, now we have a direction that it orients in. Usually they go ahead and give us the magnitude. So if we had some magnitude F equals 80 pounds. What we could then do is we could find the force vector from this position oriented out in space. So our force vector would be the magnitude of the force times the unit vector of AB. Right? So it's just rewriting these equations, rearranging these equations to get it in a form. So let's work through another example. We had done one in an earlier video, but let's work through another example, kind of get a better grasp on how this works. Okay, so I have an example drawn here to find vector F in Cartesian form. Now, the picture's a little hard to make out, so I'll try to describe it a little more. You have the white portion is a wall and then a flooring. What we have is this blue rod leaned up against the wall, so it touches both the wall and the floor. Point A is on the floor and point B is on the wall. And we have this force coming off of the midpoint of the rod at C. So what we're going to need to do is we're going to need to find the position vectors for this, then use the unit vector, convert that position vector into a unit vector that gives us the direction of F, and then we'll multiply that unit vector by the magnitude of F, so that we can get this in Cartesian. So very first things first is let's write out where all of our points are. It's a little hard to see, but here at the bottom I have 2 meters in yellow, then I've got 3 meters, and I have this 6 meters. So what these are the locations of these points. So our point A is at a location that is out by 3 along the x-axis. So our point A, this is point notation, 3. And then it goes over by 2 meters, negative. So negative 2 meters. And then our z, since it's on the floor, our z is going to be 0. There's no elevation. Now looking at our point B, we're going to find the coordinates of that. It is directly above this origin point. This is the origin point. I tried to make it a big yellow circle. It's a little bit tough to see. This is the origin point that we're referencing everything off of, which we could also tell because it's our intersection of our x, y. But this is our origin. So as we can see, our B is on our x and y 0 points. So it's going to be 0, 0, and then just goes straight up the z direction by this 6 meters length they give us. 6. So now finding each of the vectors of this is fairly easy because we're going to the origin. So the vector RA is going to be the same as the point form, and that's only because we're using the origin as the point we're going to, right? So we're doing RA is 3 minus 0, negative 2 minus 0, and 0 minus 0. So you end up with the same vector notation as you do point notation. 3, negative 2, 0. RB, exact same thing. 0, 0, 6. Now what we need to do is find the midpoint of, right? Because this is occurring at C. This isn't actually the vector we're looking for. We're not looking for this AB vector. What we're looking for is this F vector, which is going perpendicular to C. So we need to find the location of this C point. I'm going to move these A and B vectors because we're not actually going to need. What we're going to need is this midpoint. So we need A and B in order to find that midpoint. You can find it using the vectors, but instead I'm just going to choose to add these 2 points together and divide by 2. That'll give me the midpoint. So my C is that if I add these together, it's 3 over 2. Add these together, negative 2 over 2 is negative 1. Add these together, I get 6 over 2 is 3. So this is where my point C is at. Now what I'm actually wanting is this vector along this line of action here. So the line of action is the line that passes directly through the force line. It is the line that the force is acting on. So through this line of action, which is also the unit vector, line of action of the unit vector that we're trying to. So through this line of action here, it goes from C point, our C to the origin. So what we're actually trying to find here, now that we have where this midpoint is, we're going to find the position vector from C to the origin. So I'm just going to call RC for simplicity. So our RC, RC is going to be it's going from C to the origin, so it's going to be R O minus R. Right, because just like we did in our example before, RAB, RB minus RA. It's the same concept here. I could write C0, right? RC is going from C to 0. It's going to be RO minus RC. So our RO, we already know. We know that it's going to be 0, 0, 0. Right? That is the point that it is at. That's the position of it. And our RC is this guy here. So we're going to have, subtracting R0 from RC, all that does is flip the signs on all of these. So now, we have -3/2, a +1, and a -3. So our RCO, this -3/2, 1, -3. So this is our position vector. And what we'll need to do is convert this position vector into a unit vector. I'm going to get rid of this. And we had RCO was -3/2, 1, 3. To convert to a unit vector, our unit vector conversion is the vector itself over the magnitude of that vector. So in this case, I'm going to go ahead and write 3/2 as 1.5. -1.5, 1, -3, all over square root -1.5 squared plus 1 squared plus -3 squared. When I punch that into a calculator, each term divides into the top, right? My unit vector is going to be -0.43, a +0.029, and a -0.86. This is the unit vector that I'm working with. This gives me, for a magnitude of 1, defining the direction of this vector f. So the last step is the easiest step. All we need to do is multiply our magnitude of this f times this unit vector, and that will give us the vector f. If I multiply this 80 newtons to each term in my unit vector, what I end up with is, and I'm going to write this in Cartesian form instead of this bracket form. So Cartesian form is the I hat, j hat, k hat. In Cartesian form, -0.43 43 times 80 is going to be negative 34, negative 34.3 I hat plus 22.9 J hat minus 68.6 K hat. And this is the vector in Cartesian. So we're going to see this position vector pop up every now and then. And we're going to see it a lot when we use dot products in the next section. So it's important to keep this position vector in mind because it can really help you when things aren't based out at the origin.